our next speaker is Geoff Vallis from University of Exeter. So I'm sure all of you have read Geoff's book on atmospheric ocean fluid dynamics. So Geoff has worked extensively on many different areas of GFD. So today he's going to give our plenary lecture on idealized moist GFD. So Geoff, please take it away.
Hi, hello everyone, and thank you for inviting me. Just sorry I couldn't be there in Bangalore. I'm sure it's warmer there than it is here in Exeter. Yes, I'm going to give a talk on moist geophysical fluid dynamics. I put idealized in the title, but it's fainter in some ways because I think all geophysical fluid dynamics is in a sense idealized by its very nature. And I'm going to add moisture to GFD, but it's still going to remain idealized. I'm going to give divide my talk into two halves. One of them I did with James Penn, a former student here in Exeter, and it's really about a simple model of the Madden-Julian oscillation. I think you may have heard a little bit about the MJO earlier today or earlier in your meeting. And the second half of my talk, I'm going to be talking about something called Rayleigh-Bénard convection. This is work I did largely with Doug Parker and Steve Tobias at Leeds, with some recent contributions by Chris Howland at Twente, Whitney Powers, Ben Brown, and Geoff Oishi. And a shout out here to Daedalus and AFID, which are two fluids codes that we used. What is moist GFD? I think, well, as you know, I think geophysical fluid dynamics is the fluid dynamics of all things geophysical, and in particular, but not only atmospheric and oceanic fluid dynamics. I think of it also as an attempt to capture the essence of some problem, to distill it and simplify it and disregard essential details. And in that way, I think you reach understanding. So GFD is sort of a methodology as well as a subject matter. And most GFD is, as you might expect, concerned with problems in atmospheric dynamics in which moisture plays an essential role. And in the spirit of GFD, we'll seek to capture and understand the problems, simplifying as needed. It's a famous phrase by Einstein that everything should be made as simple as possible, but not simpler. Turns out that he never actually said this. The closest anyone can find to what he actually said was this rather longer statement, that it can scarcely be denied that the supreme goal of all theory is to make irreducible basic elements as simple and as few as possible, without having to surrender the adequate representation of a single datum of experience. That's not as catchy as the first phrase. Not wishing to go against Einstein, I think it's also the case that it's okay to oversimplify on the journey as you seek understanding, and then maybe you come back and add complication, or you realize what is wrong with your theory at the end of the day. In a sense, all theories are simplifications. So let me talk first about the Madden-Julian oscillation, which Fuchs and Raymond wrote, it has been and still remains a holy grail. The basic physical processes are still unknown. I think that was a little bit bleak. But at least we know what it is, and here's a picture of it, which you can find on various websites. And how it is formed is that somewhere over the Indian Ocean, convection begins. It's stormy and wet. You get a lot of convection. It generates an overturning circulation, or the simple overturning circulation. And you can understand all of this, that if it's wet and moist, you'll get convection. The thing about the MJO, of course, is that this pattern, this green arrow, then moves slowly eastward at about speed of about 5 meters per second. It passes over the maritime continent, Indonesia and so on, moves into the Pacific Ocean, and finally subsides in the Eastern Pacific. You can see here, looking at some plots of outgoing radiation on the right-hand side. Well, the x-axis is longitude, the y-axis is time, the blue is outgoing long wave radiation. So when there's a lot of blue, there's less OLR and more high cloud. And so you can see here in November and again in February and again in April, there's a propagating pattern of low OLR, so high cloud, propagating eastward. You don't always see that. In 1983-84, there were no strong MJOs. So it kind of comes and goes. It seems to come and go with a time scale of 40 to 60 days. It used to be known as, sometimes it's called the 40-day oscillation or something like that. What about its structure? Here's its structure. It's a composite made by George Kiladis. Over here on the left is the maritime continent. The blue shading here is precipitation, and the red and the green are geopotential. And the top plot is at 850 hectopascals near the surface. The bottom one is 200 hectopascals high in the troposphere. A very similar pattern, but flipped. So it's sort of got a dipole in the vertical. But on either side of the precipitation, you can see a dipole here, flow going anti-clockwise in the northern hemisphere, clockwise in the southern hemisphere. The smaller arrows, which you may be able to see, are flow being drawn into the precipitation and drawn in at low levels, being pushed out at high levels. So it's a fairly simple vertical structure. It's sort of fairly simple horizontal structure. This pattern, so it's the first baroclinic mode, if you will, in the vertical. This pattern then moves slowly eastward at a few meters per second. This is a composite. If you actually look at an isolated snapshot, it's a bit of a mess. There's convection all over the place. And if you've had basic class in equatorial dynamics, you'll know that this pattern looks rather like a famous pattern called the Matsuno-Gilles pattern. And here on the left, I've drawn specifically the pattern which was calculated by Adrian Gilles. What he did is he took an equatorial beta plane in the shallow water equations. He put a heating source at the origin, which is 0, 0 in this top plot. So he put a little bit of heating here. I hope you can see my pointer. And then this pattern emerges. It looks rather like the pattern of the MJO. You've got convergence here and here, and the air flowing towards the heating at the equator and detours around these lobes, these extratropical lobes. These extratropical lobes are called Rossby lobes. They're similar to a stationary Rossby wave. And here, this pattern extending eastwards is a Kelvin mode, which is confined to the equator. The vertical velocity in the lower plot is virtually coincidental with the actual heating itself. So this pattern below is where the heating is. So that suggests that in some ways, certainly simplifying considerably, that the MJO is similar to a propagating Matsuno-Gilles pattern. So let's pursue that a little bit. And of course, now we begin to understand why the MJO might occur at the equator. If the heating is off the equator, the pattern is rather weaker and the flow doesn't converge as much toward the heating. It tends to flow around the heating because it's in geostrophic balance. So off equatorial heating is less convergence and a stronger rotational flow. The MJO has got this rather well-known spectral diagram, now called the Wheeler-Kiladis diagram. You're plotting frequency of the y-axis, zonal wave number on the x-axis. You can see Kelvin waves up here on the left-hand plot, some Rossby waves here to the left-hand side of the plot. And here, down near the origin of the left-hand plot, you can see a signal which doesn't correspond to any simple wave like a Kelvin wave or Rossby wave. It's just has a low frequency and a large scale, and that's the signature of the MJO. So what are a few key observations for the MJO? Where does the moisture come from? Observations show that it is moisture convergence from afar brought in by the winds and not local evaporation, which is actually the source of the moisture in the precipitating region. Furthermore, if you actually look at the thermodynamic budget, the condensational heating is actually the largest term in the thermodynamic equation, rather than something like radiation or sensible heat fluxes from the ocean. Of course, there's been lots of previous work on this, and I think some seminal papers were from David Raymond, and he coined the words moisture mode, and just meaning that the MJO is a phenomena which essentially involves the interaction of moisture and the circulation. And I think that's pretty well known now that the MJO is some kind of moisture mode. What we actually mean by a mode is still up for debate. Other people have followed on, Maida and Steckman and Sobel and Maloney and others. But it's an interaction between condensational heating and the circulation. One difficulty with the MJO is that GCMs do not have a good record of capturing it. Some GCMs do capture it quite well, typically some very high resolution weather models, high resolving models can capture it, but not universally well. We're going to look in today's talk about using the moist shallow water equations. Moist shallow water equations themselves, I'll go back to a paper by Gilles, and various other people have used them, and I'm giving some references here. And our basic tenet here is that somehow the MJO is, if you will, propagating convective aggregation on the beta plane. Specifically, it's moisture driven. It's the beta plane which leads to the aggregation, so I don't really like to call it self-aggregation. And the beta plane makes it propagate eastwards. And I think what I'm proposing, which is slightly different from what others have proposed in the past, is that the propagation is really an advective propagation rather than a wave-like propagation. And it makes sense because the only thing that can move moisture is advection. It doesn't get transported in a wave-like phenomena, especially if we notice that the moisture is converging from afar. So we're trying to understand what the mechanism is. So we're going to use the shallow water equations. The most shallow water equations, which you can think of them as representing the first baroclinic mode of a three-dimensional stratified system. So you can imagine a stratified surface, evaporation is the source, they get transported around. When it's saturated, heat is released. But unlike the three-dimensional equations, we have a very simple vertical structure. Just the first bioclinic mode is represented by the shallow water equations. So we constrain the vertical structure, and that's motivated by the observations and a moisture equation. We don't constrain the horizontal structure, however. So here are the equations, just the shallow water equations. The momentum equation, the first equation familiar to people. Thermodynamic equation, which is a height equation. It's got a radiative relaxation term, relaxing it back to some prescribed value, constant. It's also got this additional term, which is a source term, which is a condensation term when moisture condenses. And so we add to the shallow water equations a moist tracer, Q. Q is the humidity. Q is advected around by the terms on the left-hand side, the convergence of Q times the velocity. Q is the humidity. And there's an evaporation and the condensation. The evaporation is, we imagine it's sitting over a saturated surface, so there's just evaporation. And there's condensation. Condensation occurs, this script H is a Heaviside function. There's condensation when Q exceeds the saturated value, which is a function of temperature. And we assume that the condensation is fast in a sense, that the time scale on which it saturates is very small. So essentially, as soon as Q exceeds the value of the saturation value, all the excess moisture is removed. And the precedents for this type of model, as I mentioned, go back to Gilles and Vladimir Zeitlin and his colleagues also pursued using this model, more for looking at things like vortices in mid-latitudes. Now, what happens if we just simply integrate this model numerically? And I'm going to show you a movie. Hopefully this will work. On the left-hand side, you're going to see the height field. On the right-hand side, you're going to see a rainfall field. We're starting it out from a saturated state, but with no motion. And we're just going to apply a perturbation to it. So let's just see what happens. Okay, we applied a perturbation here. Gravity waves propagate out. So a rainfall front propagates away from the source region. You get little spots of rainfall. Gravity waves are propagating all the time. So the whole system now just keeps on going. It's an excitable system in the language of applied mathematics. You get these condensational fronts which propagate. Rain falls out. They excite gravity waves, which leads to evaporation, more convection, and the system keeps going. But it doesn't, of course, look like an MJO. All of these spots of rainfall are propagating eastwards, westwards, northwards, and southwards. The gravity waves are propagating all over the place. What is happening? So let's repeat this, but let's now do the simulation on a beta plane. And again, we're looking down on it. The y-axis is latitude, the x-axis is longitude. The 0, 0 is the equator. I'm going to provide a perturbation here off the equator, so it's not particularly perturbed at the equator. And let's see what happens. Okay, again, we get gravity waves propagating away, gives us condensation. Looks like it did before, but now, hold on, it's starting to look a little bit different. There's less rainfall in the tropics here between plus 0.2 and minus 0.2. And now look, these rainfall bands are now propagating eastwards, rather like the MJO. So in some sense, this very simple system has captured an essence of the MJO. And this, well, we have periodic boundary conditions in the X direction. So this band of rainfall now it actually will just continue propagating eastwards. It's about to disappear here, but it will reappear here. It's converging moisture towards it, which is then condensing, causing more evaporation up here. There's only one MJO at any given time because all the moisture is converging towards this rainfall band and it's too dry everywhere else for another MJO to form. So let's try and figure out what's going on here. Here's just a snapshot. Say steady eastward propagation at about 5 meters per second. Speed's dependent upon various condensational parameters, but it doesn't depend so much on the actual speed of Kelvin waves. And the width of the latitudinal width of this propagating region is actually dependent upon the equatorial deformation radius, the square root of beta over c. So let's go back to the Gilles pattern, see what we can see. Here's the Gilles pattern. Let's put moisture in, see what that does. Here's the saturated specific humidity corresponding to the Gilles pattern. Now, let's look at how moisture converges. If you look at the right-hand plot first, the blue is from a simulation. The blue pattern is actually the humidity. These arrows here are velocity arrows converging, and they're converging to this central point, the origin, which is where we put the heating in. But let's look at the convergence of moisture. The center of convergence of the moisture is actually slightly different from the center of convergence of the velocity. It's just displaced ever so slightly eastwards because moisture has to go around the Kelvin lobe, and the moisture is also dependent upon the height field. So the moisture converges slightly eastwards. That's where the moisture converges, then that's where the precipitation will happen. Precipitation, of course, is not just determined by the convergence of moisture, but that is certainly a major factor in determining where precipitation happens, especially as in the MJO, as we've seen, that it's the moisture flux from afar which determines the precipitation. And again, here's just another plot of the same thing. I've just looked at the bottom plot. The red arrow, the red curve is the convergence of the velocity. The dashed blue curve is the convergence of the moisture. And we see it again here, repeating myself here. So what happens is that the moisture, let's suppose that this blue oval here is where convection initially starts, perhaps because the sea surface is warm. It draws moisture in, but that moisture converges slightly to the east of where the original convection occurs, and hence condenses there. As it condenses, it forms a new heat source. So it creates a new Gilles-like pattern slightly to the east of the original convection pattern. So the convection pattern moves slightly eastwards. It creates a slightly new Gilles pattern, and so the whole pattern moves eastwards in a sort of a quasi-steady way. So here's another picture of it. Air is flowing in, moist air is flowing in, some of it is flowing round the Gilles pattern. It's coming in, the air coming in from the west is drier, so the convergence is slightly to the east of the original pattern. So the whole thing moves slightly eastwards. And here's another picture looking sideways on. Now this is Z against X. Moisture's coming in from the east. It's condensing, it's rising, flowing back out again. The moisture converges slightly to the east of the initial spot. So, and hence it goes on. If we make the sea surface temperature warmer in the Western Pacific or in the Indian Ocean, that is where the pattern will originally begin. So the genesis of an MJO will begin where the sea surface temperature is warmer. And here's I'm plotting the position of the MJO as a function of time here. And MJO events will form here, propagate eastward, then a new MJO will form here. And you see this recurring pattern. Why is it at the equator? Because equatorial aggregation via the beta plane, the Matsuno-Gilles pattern, occurs there. Off-equatorial disturbances will generate rotational pattern. And why is it eastward? Because it produces convection with moist unstable air coming from the east. We can make a toy model of it, but I think I'll skip that in the interest of time. But as I say, it's a form of convective aggregation and on the beta plane. And I think what I'm arguing here is that the speed of the MJO is in a sense an advective one related to the actual fluid speed and not related to a wave speed in the sense that a Kelvin wave speed is. Okay, perhaps why don't all GCMs get MJOs? Although the mechanism is simple, as I think I've explained, turns out even when we're integrating these most shallow water equations, that the emergence of an MJO is a little bit sensitive to the actual parameters that you use. It depends upon the nature of where convection actually occurs relative to the existing convection. If, for example, your convective parameterization triggers convection too easily, the pattern may not move. It may move too fast or too slow, or parameterization that is too active everywhere will just lead to spots of convection and no organization. So it is rather sensitive to the convective parameterizations, as various investigators have found that it's dependent upon things like the entrainment parameterization. So your convective parameterization needs to be just right, or alternatively, you need to have a high resolution model which gets things right. Let me just switch gears now and talk for 15 or so minutes about another idealized problem. Perhaps just to say, I'm not arguing that this is the last word, and of course it needs to be demonstrated, and I think what we need from a simple shallow water model like this is a path to realism, and we need to try and identify this mechanism, in a sense, with a hierarchy of models, making this model perhaps more realistic by adding layers to it, and or at the same time simplifying a general circulation model to see if this mechanism will emerge in a general circulation model. Let's talk about Rayner-Bénard convection. What is Rayner-Bénard convection? It's the simplest addition to Rayleigh-Bénard convection that includes the effect of moisture. Those of you who perhaps come from an engineering or an applied math background will know that the most studied form of convection is actually Rayleigh-Bénard convection. If you do a search for Rayleigh-Bénard convection on the Web of Science or Google Scholar, you'll find thousands and thousands of citations. Rayleigh-Bénard convection is just a dry Boussinesque fluid between two plates heated from below. It's a canonical problem. People study heat transport, the transition to turbulence. It's a simple system with complex behavior, but from the atmospheric point of view, it is perhaps too simple. Atmospheric convection occurs in a compressible fluid with internal heating. And most importantly, there's moisture. That's a complex system with complex behavior. So what we are trying to do with the so-called Rayner-Bénard convection is to bridge the gap, that it's the simplest addition to Rayleigh-Bénard convection that incorporates the effects of condensation. And you can see here on the right is a nice plot of real convection. On the left is a plot of Rayleigh-Bénard convection, with the three main differences: moisture, some internal heating, the atmosphere is compressible. What we're going to do is take Rayleigh-Bénard convection and just add moisture to it. So let me skip that slide. I think I've said all I need to do. So let's put some equations up. We're now going to take the three-dimensional equations, the momentum equation, the advection, pressure term, a buoyancy term, a viscous term, mass continuity equation. Here's a buoyancy equation. Buoyancy in an ideal gas, you can think of it just as potential temperature, G delta theta over theta naught. So there's a buoyancy, advection, plus again a condensational term. And so we have a condensate, which is moisture. That's advected around here. So all the extra terms are in red. It's diffused and it condenses. When water condenses, then it provides a heating to the buoyancy equation. We're again going to assume fast condensation. So condensation only occurs when Q is greater than some saturation value. And this saturation value is, simplifying the Clausius-Clapeyron equation a little bit, it's just a function, an exponential of temperature. And it's an exponential of real temperature, not potential temperature. Buoyancy is potential temperature. So this temperature is the buoyancy, so minus beta Z, where beta is just the dry adiabatic lapse phase. So this is essentially the familiar relationship between temperature and potential temperature in the atmosphere. They're related by the dry adiabatic lapse phase. You get various then different new parameters. You get the exponential growth alpha, the exponential growth of moisture with temperature. That's occurring in here. It's one of the classic Clapeyron equations. This term beta, which is like G over Cp, it's the dry adiabatic lapse rate. And then this gamma, which is the latent heat of condensation in this system. So these are, in a sense, three new parameters, and the Rayleigh number was our original. And we can imagine, unlike in a real atmosphere, thinking of a transition to a dry system. Turns out there's a conserved quantity, which is very similar to the equivalent potential temperature of a moist static energy. We can now find, we can go further with this model than we can with a, with a full cloud resolving model using the full equations of motion. We can find some exact solutions. For example, in Rayleigh-Vaynard, there's a famous solution, which is Rayleigh's conductive solution, which is just that heat is conducted from the bottom plate to the top plate without any moisture. We can find the analog of that in the moist system by supposing that the diffusion is balanced by the condensation. With a little bit of mathematics, we find out what this solution is, which turns out we can find analytically. For the applied mathematicians amongst you, it turns out that the solution can be given analytically in terms of something called the Lambert W function. And here's a typical solution. We call it the drizzle solution. Moisture is just diffusing in. This quantity here, which is the buoyancy plus gamma Q, is the equivalent of the equivalent potential temperature, so that's diffusing in it as a linear profile. Q falls off almost exponentially with height. The buoyancy increases with height. We can find other solutions if we don't have a saturated boundary. If the flow is not saturated, the buoyancy and the moisture both diffuse independently and have a linear profile. They reach a height where it starts to condense, and then they have slightly different profiles. Can also find things like what the adiabatic lapse rate is, the equivalent for the adiabatic lapse rate with a little bit of algebra. And well, let me just give you an idea of what the phenomenology is. So we're now going to numerically integrate these equations. What these panels are from the top down: the buoyancy, the humidity, the temperature, and the velocity. Probably easiest if you just look at the top panel. We give it a tiny perturbation here. What you'll see is a plume generates. That gives rise to gravity waves which spread out, which then trigger other plumes, and so on. Let's just watch. There's a plume, more plumes. And now what actually happens is some of these plumes disappear or they merge, and we're left with a smaller number of plumes going all the way to the top. The reason is there's a separation between the two plumes because these plumes are drawing moisture into them. So between the two plumes, there isn't enough moisture to give rise to an instability. So there's a finite number of plumes. We can just watch that again. Many plumes initially triggered, then these plumes merge or disappear. And we can now look at things like how dry instability compares to a moist instability. By changing some of the parameters in the system, in particular the gamma, which is the latent heat of the latent heat of condensation, beta, which essentially is the dry adiabatic lapse rate, we can, and I won't go through the algebra, but we can find regimes which are specifically moist, unstable, but dry, stable. And we can then compare what the instability is like when the Rayleigh number, which is the overall measure of instability, is held fixed. So for a given Rayleigh number, depending on whether it is dry stable or just moist unstable, we can look at the evolution. And here's a little regime diagram of beta, the dry adiabatic lapse rate, gamma, the latent heat of condensation. We can pass between a dry, a purely stable state, a state which would be dry if there were no moisture, but is moist unstable, and which is unstable. And we can also find, this is in a recent paper by Brown and Oishi, who looked at the linear stability properties of the system. They plotted the growth rate as a function of wave number. This is a purely dry, unstable state, so it's like a Rayleigh-Bénard system. The growth rate is only positive for a small range of wave numbers. Do this for the moist system too. The dashed lines, or the solid lines are dry stable but moist unstable. The dashed lines themselves are dry unstable. Similar stability properties, linear stability properties for both the dry and moist systems. But the nonlinear properties are quite different. I think it's perhaps focus your eyes on the bottom panel here. We're changing this parameter beta. And for beta equals 0, the system is dry unstable. So this is like a Rayleigh-Bénard convection. And this is an equilibrium state. We've got convection all over the place. Over here, it's only unstable if there's moisture present. And when there is moisture present in the nonlinear integration, all of that moisture, instead of there being convection everywhere, that convection aggregates into a single large plume at this location here. So if you will, convective aggregation is occurring in a very simple system without any of the complications of radiation. Here it is again. And when it is unstable, this quantity, this blue plot here, is actually the equivalent of the moist adiabatic lapse rate, and it's more or less constant here in an updraft. The flow has relaxed to a moist unstable system. So let's look at a few movies to finish up, just to see what is happening. Here's a couple of movies. The same, we're going to look at the vertical velocity. The same system in a small domain and in a large domain. And the red is upwards velocity. And you can see in either of the plots, the upwards velocities, the plumes, will slowly just merge. And you'll get these wonderful patterns. They'll keep on merging And now in this larger domain, after a while, they'll stop merging, and you'll have a pattern of updrafts. The updrafts themselves are unstable, and they're rotating. We haven't identified the instability there. But we start out with a large number of plumes, and again, they merge because in the space between the plumes, it's too dry for there to be convection. We have yet to establish what the form of instability is, which is giving rise to these little rotating clover leaves. Nor do we have a theory for the spacing between the plumes, which we would like to have. But we think that kind of thing is actually approachable in a system like this. Show you a couple more movies before finishing up. Looking at vertical velocity, moisture, and buoyancy. Depending upon the parameters which we choose, we can get rather weird and wonderful patterns. But again, we see typically the updrafts merging, and we get a smaller number of patterns finally in the end. Here's a plot of rotating convection, this movie by Whitney Powers of University of Colorado at Boulder. We're looking at the buoyancy on the left, and the relative humidity on the right. It organizes itself into patterns. Here now, all of the little individual cyclones are spinning in a particular direction. The rotation has introduced a cyclone and anticyclone asymmetry. And in this particular state, we've formed if you will, a crystalline state. So it's a very rich system, and we've only begun to scratch the surface of the dynamics. But our hope is that we can at least start to understand some things and get theories for what determines the plume separation, what determines the nature of the instabilities of the plumes, and so on. Many unsolved problems. As I say, we don't have an analytic linear theory of this drizzle solution. I don't know whether it's possible or not. Certainly would be difficult to do. Some people are started to investigate this. Some possible progress by a group of people, including Paul Curtis, a student at Yale. If we take the limit, the fast condensation limit of tau going to 0, you can show that in some circumstances, precipitation just will occur when the vertical velocity is greater than 0, as you might expect. And then you don't need a separate moisture equation. You can just add a term, the source term, to the buoyancy equation, which is proportional to the vertical velocity, which is only positive when the vertical velocity is positive. But there's many unsolved problems, more problems than solutions. The linear stability, convective aggregation, the notion of subcritical instability, meaning that you can probably sustain convection, or possibly sustain convection, even when the state is linearly stable, because the convection itself provides a finite perturbation, which triggers more convection and maintains the convection even when the linear state is stable. Whether that occurs or not is an open question. One thing I think would be nice too would be to have a low order system, rather like the Leven's 1963 system, but with moisture. And of course, with all of this, one would like to have a pathway to realism, because again, we have a simplified system. People who study the real atmosphere would probably say that it's oversimplified. But one would like to perhaps begin with a system like this and have a path to realism by adding compressibility, adding some radiation, and adding cloudiness, which is liquid water that doesn't fall. So I think that's all I have to say. So I will stop there and thank you for listening, and I'll be happy to take any questions.
Thanks for the nice talk, Geoff. Do we have questions from the audience? Yes, Adrian, yeah. Can we pass the microphone?
Hi, Geoff, it's Adrian here.
Oh, hi, Adrian. Nice to see you.
I don't know if you can see on the camera, I'm over there on the right. I enjoyed your talk.
Yeah, I can see you. Yeah, you're wearing shorts. You wouldn't be wearing shorts if you were in Exeter today.
I'm doing great. Grounded myself to shorts. Yeah, no, I just wanted to go back to the first half of your talk when you were talking about the MGO model. And I noticed that when you had the very first simulation with no rotation, you had these fronts of precipitation that were kind of, small, should we say, small scale organization.
Yeah.
I'm presuming that was through the U relationship for the evaporation in the model. No, basically that was a kind of like a mini kind of wishy feedback that was causing that organization in those equations. That was only in the Q equation. That's anything, the term I could think of that would give you that kind of clustering. And related to that, I was wondering, when you put the rotation in, the convection off the equator seemed to lose that kind of clumping. It was much more isolated away from the main MGO organization. So I was wondering why there was that difference in the off equator kind of organization between the rotation and rotation case.
Okay, let me answer the second question. When I added rotation, I did it onto a beta plane.
Yes.
So there was still some rotation off equator a little bit. It wasn't necessarily zero. It wasn't a non-rotating case necessarily. So I'd have to look back to see. I don't know whether I actually spotted that difference myself. Maybe I can go. Shall I try and go back to the?
If you like, yeah. If it's not too much trouble.
Gosh. Can you see that slide?
Yes. So when you showed the first animations, I remember there was the very, very first case before you added any rotation. You said zero rotation, the very first animation. It says no rotation starting. So
okay,
here you had this kind of, the rainfall kind of stays in small clusters. And I was presuming, is that the evaporation wind speed sensitivity?
It's not actually, because there is no wishy term in here. I'm just evaporating. In this particular simulation, I'm just evaporating, locally. It's just proportional to the humidity difference between the surface and the atmosphere.
Was there not a U term in the equations? I seem to remember.
No, it's just Oh,
Yeah, you
there
have
is
E
here.
equals CDU Q surf minus Q. So
Yeah,
that
there
was
is
where I was
there is
presumably
here,
using
but I think in that simulation, I'll have to look, Adrian. I
Okay.
think in that simulation that term isn't there,
Oh,
but
okay.
I'd have to look. But I should say,
But how do you get the clumping then in that if there's no U term?
well, why? What would you expect? Would you just expect rainfall to be isolated at a grid point? I mean, there's still evaporation. It's as if U is constant. So I'm not sure I see why there shouldn't be clumping.
I would have
Another
expected
reason
sort
is
of
that,
speckled rain according to the kind of modulation of the gravity wave overlap, you know, where you have
yeah,
both
now I
of them.
should say a possible answer to your question is that when I plotted the rainfall here, I did a little bit of smoothing to make it appear a little bit nicer on the movie. So some of that clumping may be that, but I think there's more aggregation than I would expect. I think I'll have to look at what the case is in this particular movie to answer your question. Just another answer to your question is that there's a paper by Andy Maida and company where they look at some of the analytic solutions to these equations. And they argue that these equations will actually give you fronts of precipitation, like you're seeing in the bottom right-hand corner there. So that they will self-organize and just give you a front of precipitation. So
did they have U in their equation?
I doubt it somehow, because that would make it quite a horrible equation to solve. So so I'm not giving you a very satisfactory answer. So I'll have to look back and maybe email you afterwards.
Nice presentation, sir. Sir, along with
hello?
equator, both Rossby waves and gravity wave, both Rossby waves and Kelvin waves also there. But along with NI waves also there. NI waves. In the
yeah. Well, Yana waves will be there in principle. There's no reason why they would not be there.
Yeah. Like angio propagation, NI waves also any influence is there in propagation changing?
Yes, Yana waves will be there. But I think, in a sense, what I'm arguing is that, you know, if we go back to, let's just start this movie again. That we have Rossby waves, we have Yana waves, we have Kelvin waves, we have all of these waves. But the actual speed of propagation of the precipitation clumps is determined more by an advective phenomena than by a wave-like phenomena. I mean, the Kelvin waves here, for example, are moving about 4 times as fast as this band of rainfall is. So, so yes, all of the waves are there. I don't, including Yanai waves. I haven't investigated the particular importance of Yanai waves. But I'm more arguing that the propagation is sort of is more like a Gilles pattern that's quasi-steady, that it's advecting eastwards in a sort of a quasi-steady fashion, rather than being a you know, an identifiable Yanai wave or Kelvin wave or something like that.
Yes, next question there.
Thank you, sir.
Yeah. So it looks like, so I'm first I want to confirm one thing. I'm not sure, as you have written the moisture equation in the terms of moisture flux convergence, so you don't need any background gradient in this case. So most of the moistening is happening due to the moisture convergence, but there is no role, seems like there is no role of the moisture advection due to the gradient in background, which there is a lot of papers, I mean, a school of thought which thinks that MJO critically depends on the background moisture gradient. That's question number one. And the related question is, if so, then how do you think it is different from the trio interaction theory of the Wang and company, Chen and others, where they think that MJO is a moisture mode, but the moistening happens not due to advection, but rather than the moisture convergence?
I'm well. I'm not differentiating between moisture convergence and moisture advection. I mean, they're two sides of the same coin. So you know, they're both U dot grad Q is the divergence of UQ minus Q times the convergence of U. I mean, advection and convergence are two sides of the same coin. It's the advection which is leading to the convergence. So I'm not differentiating between that. But I'm saying, what I am saying is that the speed of propagation ultimately will depend upon the speed at which moisture can be advected from one place to another. So that's a fluid speed, not a wave speed. I'm not sure what the paper that you referred to actually stated in that regard. So I'm stating that this advection, that this propagation occurs because the convergence, the moisture convergence, occurs slightly to the east of where the heating is, which is giving rise to the pattern in the first instance. So I don't think I see that particular argument made in their paper, but I would have to look.
So the question is, do you, in that case, is there any critical importance of background moisture gradient in your model? Seems like it's...
Do you mean like an east-west gradient?
Sorry?
You mean like an east-west gradient?
Yeah. Yes, or the meridional gradient, whatever. Yeah.
Yeah. No, I don't have any particular importance for that. I have a homogeneous background. Now, having said that, there is certainly an importance for the east-west gradient in where the genesis of the MJO occurs. So in that sense, I would agree that it's because it's moister, more moist in the Western Pacific and over the Indian Ocean than in the Eastern Pacific. That's where that gives rise to the genesis of an MJO pattern. Once that MJO pattern forms, it will start to move eastwards. So when I have, in the first simulations that I showed, I did not have any background gradient of moisture at all. And then the genesis of an MJO event would occur more or less randomly over any particular part of the ocean. When I did put a background gradient of moisture in, then a typical MJO event would form, you know, in the region of excess moisture where it was most convectively unstable. So in that sense, certainly the background gradient is important. I mean, the background gradient is important, you know, in our common conception of what the MJO is, namely forming over the Indian Ocean, moving east over the maritime continent.
Okay, thank you. Thank you.
Any other questions? Yes, Vishal.
Yeah, thanks, Geoff, for a very nice talk. My question is about Rayleigh-Bénard convection. And so I see that in the movie that initially there are several plumes and some of them disappear or maybe merge, and ultimately you get some standard wave number. So my kind of thought goes back to the radiative convective equilibrium where the heating and cooling would balance, and that would decide the ratio of area of ascent and descent in these plumes. But you don't have any explicit radiative cooling in the system. So I was wondering what goes on in the absence of radiation.
Yeah.
Maybe you said it,
Right,
I missed it. Yeah.
No, I didn't show any. We've done some simulations, and a student of Caroline Muller has actually done some simulations adding radiative cooling to this system. But in the system I showed, the separation between the two plumes is more determined by how strong the plumes are, and the fact that the plumes will draw moisture in from the side, so that you cannot get another plume too close to the original plume, because there won't be enough moisture for it to be convectively unstable. So there's a difference there. How radiation I mean, I guess in the model that we're showing here, the analog of radiative convective equilibrium is a sort of a convective diffusive equilibrium. But yeah, that's something to be further explored, I guess.
Yeah, maybe a follow-up question on that. Is it a priori kind of guaranteed that there would be an equilibrium in the state, or it just emerges?
Do you mean a statistical equilibrium or just a steady state equilibrium?
A steady state.
Well, no, it's not guaranteed. I mean, you know, there exists a diffusive solution, which we're calling the drizzle solution, when moisture diffuses in and then falls out. Typically, that solution will be unstable and give rise to turbulent convection, which reaches some kind of statistical equilibrium. In the first plot I showed, which was convecting, it actually reached a true equilibrium. But if you make it a little bit more unstable, you know, increase the Rayleigh number or reduce the friction or something like that, it will become a convectively turbulent state, and it will just reach a statistical equilibrium. Does that answer your question?
Yes, maybe a quick, if others do not have a question, maybe I've asked a couple of already. If maybe in the meantime, I'll just, so the people have done a homogenization experiment where they've homogenized radiative cooling. So there's no gradient in radiative cooling in the whatever radiative convective equilibrium domain, or homogenization of surface fluxes and so on. In such a setup, probably, am I right in interpreting that one could just throw out radiation altogether and still you would see some organization of plumes, so far as you have convection and some diffusive process maybe through waves?
Yeah,
so
I mean,
far as you have those.
I think you will. Well, we do see some organization in the sense that the plumes become concentrated. We don't get just convection occurring at every single grid point because of this drying phenomena. So now in the real world, of course, people argue that radiative effects are in fact quite important in providing convective aggregation because of different radiative effects when there are clouds present. And that may well be true, but I think we're arguing that you can get some forms of aggregation even in the absence of that.
That answers my question. Thanks a lot.
Yeah.
Okay, I think there are no more questions. Thanks a lot, Geoff, for the nice talk. I think you have a class starting soon.
I do. I have to go and give another lecture.
Okay, all right, all right. Thanks a lot. Take care.
All right. All right. Thank you.